This is the second portion of section 8.3. We're going to find all the terms up to degree 5 in y1 and y0 of the power series solution of this differential equation. Then we're going to go ahead and solve the IVP. So the way we start all our solutions is we start by assuming y is the sum n equals 0 to infinity of Cn x to the n. Then y prime is n equal 1 to infinity n Cn x to the n minus 1. And y double prime is 2 to infinity n times n minus 1 Cn x to the n minus 2. Okay, now we plug in. So y double prime, n equal 2 to infinity n times n minus 1 Cn x to the n minus 2 minus 2x y prime, which is the sum n equals 1 to infinity of n Cn x to the n minus 1 plus 8 y, which is the sum n equals 0 to infinity of Cn x to the n, and that equals 0. All right, distribute. So I'm going to bring the 2x in, and I'm going to bring the 8 in. So the first power series remains unchanged. N equals 2 to infinity n times n minus 1 Cn x to the n minus 2, and then minus the sum n equal 1 to infinity of 2n, I'm bringing a 2 in, Cn x to the n, because I had n minus 1 plus 1 is n. Then sum n equals 0 to infinity of 8 Cn x to the n, and that equals 0. All right, reindex. All these power series have to be in x to the n. So I don't need to reindex this one, and I don't need to reindex that one. I only need to reindex the first one. So that's going to start now. I need to add 2 in the formula, so I'm going to subtract 2 down here at the base. And everywhere I see an n, I put in an n plus 2. So n plus 2, n plus 1, Cn plus 2, x to the n. And then the other power series remain unchanged. 2n Cn x to the n, and then 0, n equals 0 to infinity, 8 Cn x to the n, and again that equals 0. Combine. So I want to write this as a single power series. I need to start them all at 1. Because that's the highest value of n where we're starting. So that means I need to cull off the 0 term from the first and the third power series. So that gives me 2c0 from the first one, 2c2 from the first one, and then 8c0 from the last one, plus, now I can combine them all and start at 1, and I combine them by combining the coefficients. So, big bracket, my first coefficient is n plus 2, n plus 1, Cn plus 2, and then my second coefficient is, these are both in terms of Cn, so I've got, I'll do my scrapbook over here, I've got negative 2n Cn plus 8Cn, which is 8 minus 2n Cn. So my second coefficient here is 8 minus 2n times Cn, and close my bracket, all times x to the n equals 0. Okay. Recurrence relations. We set all our coefficients equal to 0. Now, be careful here. when we set coefficients equal to 0, I'm not going to set this equal to 0 and that equal to 0 separately. I need to set that whole thing equal to 0 because this is my constant coefficient right there. So that whole thing needs to be 0, which I did here. And then I set this whole thing equal to 0, which I did here. And now in each case, we're going to solve for the higher Cn in terms of the lower Cn's. So this one gives me C2 is negative 4 C0. And for this one, I'm going to solve for Cn plus 2. Okay, so I bring the 8 minus 2n Cn over with a minus in front of it, so I can just change the sign 2n minus 8 instead of 8 minus 2n times Cn, and then divide by n plus 2, n plus 1. Okay, so let me clean this up a little bit. Cn. Pause the video if you have to and make sure you understand what I did. I solved for Cn plus 2. That introduced a minus sign when I subtracted this whole term. And instead of writing negative 8 minus 2n, I just wrote it as 2n minus 8. Okay, so I have that, and I have this. And this guy is valid for n equal 1 to infinity. All right, now I'm going to find all the coefficients up to C5, and I want to do that and want to write them all in terms of C0 and C1. So I start with n equal 1. That gives me C, and I'm looking at this formula right here. C3 is, if n is 1, I get negative 6 over 6 C1, which is negative C1. Okay, when n is 2, I get C4 is, let's see, negative 4 over 12 C2, which is negative 1/3 C2. I'm not allowed to have C2s, only C1s and C0s. So I look up above and I see that C2 is negative 4 C0. So this gives me positive 4/3 C0. Okay, now when n is 3, I get C5 is negative 2 over 20 C3, which is negative 1/10 C3. Can't use C3 though. So looking up here, I see C3 is negative C1. So this gives me C5 is positive 1/10 C1. Okay, and I can stop there because I only have to go up to degree 5 in this next step. Okay, and so I write down the first few terms. I'm going to go up to 5, so I wrote down up to degree 5 here. And now I plug in my values of C from above. So y equals C0 plus C1x. And then C2 is, go up here, C2 is right here, negative 4 C0. So I go negative 4 C0 x squared. And then C3x cubed. C3 is negative C1. All right, now degree 4, I want C4, which is positive 4/3 C0, x to the 4th. And then finally, C5 is 1/10 C1, and that's x to the 5th, dot, dot, dot. Okay, so now I want to write this as my C0 terms and my C1 terms. So factor out a C0 and write down all the terms we get that have a C0 in them. So 1 minus 4x squared, that's this one, and then plus 4/3 x to the fourth, that's this one, and that's all I have. I'll just put plus dot dot dot. That's all I have for now with a c naught in it. And then c1, I'm going to get x. This guy's got a c1 in it, so minus x cubed. And then this guy's got a c1 in it, plus 1/10 x to the fifth, dot dot dot. All right, so if I were just finding a power series solution up to degree 5, I'd be done at this point, and I would circle that and move on. But we want to actually go a little further. We want to solve the IVP. Y of 0 is 3, and y prime of 0 is 0. So we're going to use our answer. First, let's find C naught. Let's use y of 0 is 3. Okay, so in this formula here, I put 0 in for x. Y equals C naught. And then the only term that lives is a 1 because everything else is 0. And then in the second portion, everything gets killed off. 0. Oh, sorry. On this side, instead of y, I want 3 because y of 0 is 3. So I put 3 in for y and 0 in for x. And I see that C naught is 3. Okay, so then, oh, I see I put the solution here again. So put a 3 there. It's sloppy notation, I know. I should have just written it down again. Now, I'm going to find y prime of x, and then I'll use the initial condition y prime of 0 is 0. So to find y prime, literally take the derivative of every single term. So, oh, sorry, I'm working with this. They're the same thing though. So find y prime, take the derivative, we get 3, and then the derivative of 1 is 0. The derivative of 4x squared is 8x. The derivative of 4/3 x to the fourth, bring a 4 down. And we're going to get 16/3, and it's positive, x cubed plus dot dot dot. And then over here with my C1, I get plus C1, take the derivative of every term. The derivative of x is 1. And then the derivative of x cubed is 3x squared. And the derivative of the next guy is going to be 1/2 x to the fourth, dot dot dot, that's enough. Now plug in the initial condition that y prime of 0 is 0. So that gives me 0 equals, everywhere I see an x, I put in a 0. So 3 times 0 plus C1 times, all these terms die except the 1. So C1 times 1. So this tells me that C1 is 0. So now take those initial conditions, those values of C, and put them back into that red formula to get y equals 3 times 1 minus 4x squared plus 4/3 x to the fourth plus dot 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 plus nothing because C1 is 0, so that whole second portion gets obliterated. So if I want to write that a little cleaned up, oops, y equals 3 minus 12x squared plus 4x to the fourth dot dot dot. And that is the solution to the IVP. Notice there's no constants in there. So you're doing it just like you would solve any other IVP. You're plugging in the two values. It's just that instead of now having a polynomial, we have an infinitely long polynomial. But the process is the same. The next video, I will do the next example. So you can definitely do that before the next video. I hope you're getting it by now. But try it on your own and then watch the next video to see how you did.